All right, anybody have any homework questions? Today I want to just put a structure up here and let you work through it together all the way through the internal loads, so you're using those rotation matrices. Before I do that, quiz 2 is this Friday. So remember to read through your notes, review your notes. All right, well, let's go. So let's have a structure like this. Let's say that's 500 newtons. At the midpoint of this one, let's apply a force of 1,000 newtons. Let's say that these angles are 20 degrees from, so 70, I guess. And the lengths are 2 meters. And the masses are 40 kilograms. No. Let's not do the, so if I put the masses in there, what would it add to this problem that you haven't done homework problems on? Yeah, right. It would add that distributed load, and then you'd have to do the rotations of distributed loads. Let's not worry about that. So let's just neglect the masses, and we'll just work with this. Okay, so let's call this body 1, body 2, ABC. And let's start with body 1. So feel free to work together, but let's take a couple minutes, draw the free body diagram, come up with the equations for body 1. We'll go to body 2, and we'll just sort of step through this piece by piece. For the first body, we have, come on. A reaction up there, I'll call it RA. Down here, we have the force on 1 by 2. And then we're assuming that the pin is part of this body, so the 500 is here. I'm going to put my about point up here. So for the force RA, the row vector is 0. The force is RAX, RAY. Moment is 0. Then the force F12, that row vector is 0.684, 1.88. Is that what everyone else got?
Yeah.
Force vector, this is negative 1.88, sorry. Force vector is F12x, F12y, and the cross product is 0.684 F12y plus 1.88 F12x. And then the 500 Newton force Same row vector, 0.684, negative 1.88. Force vector is 500, 0. And so the cross product is positive 940. And so we get three equations. The first one is RAX plus F12X is equal to negative 500. Second one is RAY plus F12Y is equal to 0. And the third one, reordering it, 1.88 F12X plus 0.684 F12Y is equal to negative 940. Everyone good with that? Okay, now go on to body 2 and get those equations. Okay, so body 2. We have RC up here, a 1,000 Newton force at the midpoint. Down here we have negative force on 1/2, and we're not counting that 500 Newton force there. I'm going to put my about point down here. So I'll start with negative F12. The row vector is 0. Force vector is negative F12X, negative F12Y. Cross product is 0. The 1,000, the length of this whole thing is 2 meters, so it's 1 meter from the about point to the 1,000. So that row vector is 0.342, 0.940. The force is negative 1,000, 0. So the cross product is positive 940. It
would be negative because isn't
Negative.
it'd be negative.
Yeah, it's 0.342 times 0 minus 0.94 times negative 1,000. So it comes out positive. And then RC.
Sorry, you were. I had my about one.
Oh, yeah. RC, so that is 0.684, 1.88 for the row vector. Force vector is RCX, RCY. Cross product is 0.684 RCY minus 1.88 RCX. And so equation 4 says negative F12X plus RCX is equal to positive 1,000. Equation 5 says negative F12Y plus RCY is equal to 0. And then equation 6 says negative 1.88 RCX plus 0.684 RCY is equal to negative 940. Okay, so the next step is, so solve this system using reduced row echelon form or whatever you want to use. And then once you have that, draw the free body diagrams of each of these two bodies with the external loads on them. Okay, so that's the next step. Okay, and then so everyone has different calculators, but yeah, so I guess I won't go into how to do it with the calculators. That stuff is in that text document on D2L if you want more details. But so now we're going to go this Q times the vector in the old coordinate system of 500, 0. That's what we're going to do to transform both of these two 500 Newton forces on the ends. And that gives you 171.01, negative 469.85.
Question.
Yeah.
When you're doing this, you can choose to not do one endpoint because you'll never reach it.
Yeah, that's right.
And you can decide which one by which of the two horizontal rotations to make.
Yes, exactly. So since we always work from the left end, I guess we need the one on the lower left end, but we're never going to get to the one on the upper right end. Yeah, that's right. And then at the middle, we had a force of negative 1,000, 0. And that came out to negative 342.02, positive 939.69. And so now we can represent this beam in the orientation we're used to. So we have 171.01, negative 469.85. And at the midpoint, we have negative 342.02, positive 939.69. And then at the end point, the one that you're right is not going to come up in the internal loads is 171.01, negative 469.85. Okay, well, now that we're done with all the coordinate system transformations and everything, this is about as simple internal loads problem as you can have because we don't have any distributed loads or anything. How many cuts do we have to make?
Just two.
2. Yep. So now take a couple minutes and calculate the internal loads on that first cut. So for cut 1, this is for x values between 0 and 1. We have the force at the end point of 171.01, negative 469.85. And then we haven't gotten to that midpoint yet, so the only other loads we have are T, V, and M. Newton's second law says 171.01, negative 469.85, plus T negative V is equal to zeros. So T is negative 171.01. Is this in tension or compression? Compression, yep. And V is equal to negative 469, that's not a 9, 469.85. And then the moments, we have M, my about point's over here, so those don't produce anything. M minus Vx is equal to 0. So M is equal to Vx. So M is equal to negative 469.85x. Okay, and now do cut 2. So cut 2 is for x values from 1 to 2. So over here we have the 171.01, negative 469.85. A meter away, we have these forces, negative 342.02, 939.69, and then we have the internal loads. So Newton's second law says 171.01, negative 469.85, plus negative 342.02, 939.69, plus T negative V is zeros. So T is equal to positive 171.01. V is equal to positive 469.85. And then the moment equation, where that's the about point. The x component doesn't produce any moment. The upward force of 939, that's a counterclockwise moment with a moment arm of 1. So we have 939.69 plus m minus Vx is equal to 0. And so m is equal to 469.85x minus 939.69. Anybody have any questions about that? Okay, we have a couple minutes. Let me show you something real quick that's okay. So I talked a little before, I haven't made you spend any time using truss simplifications, but I talked about what it was. How would things change if you had this same shape These are still 70 degrees. We had the 500 Newton force like this. but we didn't have that 1,000 Newton force. Okay, and we're neglecting the masses, we're neglecting the weights. The lengths are still the same. And we want to calculate the internal loads. This problem looks pretty similar, but now each of these bodies has only 2 forces on it. So we can treat this as a truss. So I'm just going to isolate that pin B. And if I call this body 1, this body 2, A, B, C. Then the forces at B are, I'll call this F1, F2, and then 500. Okay, we only have 2 unknowns, so we can solve that by just treating this as a particle. So we have negative 0.342 F1, positive 0.940 F1, plus positive 0.342 F2, positive 0.940 F2.
These are unit vectors.
Yes, those are just unit vectors in the direction of those. We're doing this exactly as if those are cables. It's just that we can get positive or negative answers in the end. And then we have plus 500, 0 is equal to 0. So F1 is equal to negative F2, and we get that 0.684 F1 is equal to 500. And so F1 is equal to 730.99. And F2 is equal to negative 730.99. Okay, so let's think about free body diagrams of each of these 2 bodies. Okay, so what does it mean that we get these values? Well, remember that we know a 2-force body just has forces along the line between the 2 forces. So F1 has a force going that way of 730.99 and a force going that way of 730.99. So that one's in tension. Body 2 is in compression with forces of these same magnitudes. So what do you think the internal loads are for that? I mean, you could go and do the coordinate system transformations, do the cuts. You need 1 cut for each one. But what you'd get is, well, what does it look like is happening to a member that's a 2-force member? The whole idea of a 2-force member is it's either in pure tension or pure compression. And so this one, if you did the internal loads, you went through all the coordinate system transformations, you'd get T is equal to positive 730.99. This one, you get T is equal to negative 730.99 because it's in compression. Okay. So remember that about, as we're talking about internal loads and everything, remember that the whole idea of a truss is it's just in tension or compression. That tension that you calculate for a two-force member is the internal load. There's no shear forces, no bending moments, anything like that. Any questions about that? Okay, so if you see a truss, you always know you have this situation for the internal loads. Just tension or compression, nothing else. Okay, that's all.